Hi everybody, welcome to this section 2.1 video. Well, we're going to be learning about solution curves without a solution. So let's read the introduction to get an idea of what this topic is really about. So suppose that we have a first order differential equation, just some generic differential equation. Okay, dy over dx equals some function of x and y. Okay, so suppose that we can neither find a solution to this differential equation or even invent a method for solving analytically. Okay, so how would we figure out how to solve this? So in this section, we learned of a mathematical object called a direction field that allows us to see solutions graphically. Okay, so maybe you've seen this in calculus 2. Okay, maybe you have, maybe you haven't, but that's why we're relearning it again today. But that is the topic of this material. So let's look through the learning objectives and see what exactly we're going to be learning today. So we're going to define direction fields, solution curves for first order differential equations. We're going to use technology to draw these direction fields for a given differential equation. We're going to use a direction field to draw solution curves, and then we're going to define and find equilibrium solutions for a differential equation. So before we even get started with the direction fields, let's just define a couple of things and see how a direction field is essentially developed. So slope. All right, we're talking about differential equations, we're talking about derivatives, so slope is heavily involved in these direction fields. So consider the first order differential equation. Once again, it's our generic differential equation. And so the function that's in terms of x and y is called the slope function or rate function. Okay. So the slope of the tangent line at some generic point x and y on a solution curve is the value of the first derivative at this point. And we know that this value would be if we plug in this point x and y into that slope function. So if we plug in our points x, y into our slope function, we will get some type of slope and tangent line. Okay, makes sense. So now suppose that the point x, y represents any point, okay, not just itself, but any point in the xy plane for which the function is defined. So the value of f of xy that the function f assigns to the point represents the slope of a line. It's also a line segment, and we like to define this as the lineal element. Okay, so for any point, we can get some type of lineal element, which means slope. So if we plug in a point into our slope function, we get some type of slope or line segment. It looks like this, like a positive slope. Okay, it could look like this, could be a negative slope, or we could have no slope. It's just a flat line. So for any given point, we can have a positive, negative, or no slope at all. So let's look at a quick example and not just arbitrarily talk about a lineal element. Let's try and see one through calculations. So Consider the differential equation dy over dx equals 0.2xy. We want to find the linear elements at 2 comma 3. So what we would want to do here is plug in the point 2, 3 into our differential equation. So I'm plugging in 2 and 3. Because remember, this is just a point. So I'm plugging in x and y, and what I'm getting is a slope of 1.2. Positive number, so that means I have a positive slope. Okay? Now, graphically, say I want to, this is the part of our slope field. Okay? Here at the point 2, 3, 1, 2, 3. Here at the point 2, 3, I'm going to have a positive slope of 1.2. So that means my slope on the slope field at this specific point would look like this. Okay, so we have an idea of a slope at one specific point. So let's keep building on this and see how it relates to a direction field, which is also the same as a slope field. Okay, so let us carry this idea of a linear element at any point in the XY plane. So if we find the linear element at every single point, okay, we're finding the slope at every single point, then the entire collection of all these small slopes is what's called the direction field or the slope field of this specific differential equation. Okay, so if we find the slope at every single point for the differential equation, we come up with a slope field. Okay, and the purpose of this slope field or direction field is that it provides a shape of a family of solution curves for that differential equation, which means that it can give us some possible solutions. Okay, and the way it gives us some possible solutions is that a single solution curve that passes through a direction field must follow the flow pattern of the field. Okay, so let's look down below at the differential equation we were just working with in this example. So below is a direction field for the differential equation dy over dx equals 0.2xy. So this is a slope field for the differential equation. We already calculated one slope from above. We saw like this was that point at 2 comma 3, right? That was the slope we had at the point 2, 3. Let's look at another one. Let's look at like 2, negative 2, 4, for example. Let's look like right here. Okay, off to the side, let's say like at negative 2, 4, we're going to plug in our coordinate point. That ends up being negative 1.6. So I have a slope of negative 1.6. So yeah, I have a negative slope here at negative 2, 4. Okay, and this slope field is just a generation of all these different points and their slopes. Okay, so now when we talk about a solution curve, we can talk about through any specific point, we can obtain a solution curve. So for example, if I look at the point zero, uh, let's look at 2, -2, okay? I can create a solution to this differential equation at the specific point, much like an initial value problem. All I must do is follow the flow of the direction field. I'm following the tangent lines. So I would just need to make sure I'm following the flow of the slopes. So it looks something like this. Okay, so that would be a solution at 2, -2. So solution curve at 2, -2, much like an initial value problem. And we could do that for basically any point here. Okay, so it is important that we understand the concept of direction fields and how to apply them, but it is not necessary to draw them by hand. Okay, so drawing them by hand is a very old and, useful method. It's actually called like the method of, oops, method of isoclines. Okay, and it's where you just sketch out a direction field by hand. Maybe you go like 5 by 5 or 10 by 10. Method of isoclines. So you know what's useful? You're going to get your calculations hopefully done correct. When I was in school, we used to do this to some extent. Like on exam, it would just say like draw a direction field and draw a solution curve at this point. But it's a bit outdated. We have so much technology now that we don't need to spend too much time doing that, although it is useful in understanding how a direction field works. But we have a couple of texts to mainstream the process. So here I provided a couple of links. They're also on Canvas. Okay, and then here are GeoGebra and Desmos links. So let me click on this GeoGebra link right here. So let me open the link. And then here you have an application to draw a direction field for any differential equation. So the differential equation we were looking at was 0.2. So you just type in the slope function here, 0.2, and then xy. And then it'll refresh and then draw your point. So here's a direction field that we're just looking at. This is what I have in the notes. Just took a screenshot. So the point that we draw a solution curve for was like 2, -2, I believe. So all you got to do is just drag it, and then this is what we drew on our paper. Okay, so use it as a tool. There's also another app I have for you provided, which is the Desmos slope field. I personally prefer the GeoGebra one instead, but you could just type in your slope function here. Again, we could do 0.2 xy, and it's the same slope field, just a lot more colorful. But I do prefer the GeoGebra one. I think it's easier to work with. Okay, so those are your two resources. Once again, they are on Canvas to use. I recommend using them for homework. So recommend using for homework and just playing around with. Okay. So let's go ahead and try an example, example 2. And so here use a direction field to sketch an approximate solution curve to the initial value problem. So here is a differential equation put on GeoGebra, dy over dx equals sine y. We have an initial condition, y of 0 equals -3/2. So we can't solve this analytically. We haven't really learned any tools to solve it analytically, but we can solve graphically with solution curve. Okay, so solution curve, we want to pick that up. So what I want you guys to do is pause the video, see if you can answer this with a solution curve at the point 0, -3/2. So pause it and then we'll come back and hopefully you tried it out. Okay, welcome back. So hopefully you tried this out. Hopefully you got it correct, but if not, we'll go over it. So we want to find a solution curve for this differential equation. So the specific initial condition that we're looking at is 0, -3/2. So that is 0, -1.5. So that would be right down here. And so we want to solve by using the solution curve. So, this is something that to do, you have a couple steps you got to follow. So we must follow the flow pattern of the field. Okay, so think about it as like a river. We got to follow the flow of the river. So follow flow of river, wherever the current's taking us, okay? And the second thing we got to do is we got to be tangent to the lineal element. Okay, so let's see where this point takes us. So let's zoom in. Okay, so it looks like it's taking us all the way down here, but then we're kind of hitting a wall down at -3. Okay, now let's go up above. Let's see where our slopes are taking us. Let me start that over. Okay, and then, yeah, we're hitting a wall at 0. Okay, so that is our solution at 0, -3/2. And so we could verify this. Maybe you didn't draw it too correctly, or I didn't draw it too correctly. Uh, we can just go back to our graphing utilities and see if we did this correctly. So let's go to GeoGebra again and see how fair our estimation was. So our differential equation was sine of y. So let's see our function, sine of y. Let's see if that works. Okay. And then our point was 0, -3/2. Okay, so pretty close. I can't get it right on the point, but we're fairly close, so our estimation is okay. So with that being said, that is essentially how we draw solution curves. Okay, so like you're doing this on your own, just make sure you double check your work and make sure the curve looks correct. So that's it for this video, and I'll see you in the next one. Okay, take care.